going to solve the same problem. We have a prop cantilever beam with a concentrated load at midspan of 160 kilonewtons using method of consistent deformation or superposition method with one redundant. This time we're going to consider M sub A as our redundant. So again, this method is applicable for indeterminate structures. So the first thing that we have to do is to check for the degree of indeterminacy if it is really indeterminate. So that would be reaction minus equation minus the number of condition. So for this case, so since this is a fixed support, so we have vertical reaction, horizontal reaction, and we have a moment reaction. So we have three reactions here, and we have a roller support, so we have a vertical reaction there. So we have a total of 4 reactions, and we have 3 equations of equilibrium. And since we don't have any internal hinge on the beam, so there will be no additional condition. So 4 minus 3, so that means it's 1. So 1 means first degree indeterminate. So for first degree indeterminate, we have to choose one redundant. Okay, so this time I'm going to choose the moment at A to be my redundant. So how do we do it? So first we have to draw the primary structure. Okay, so the primary structure consists of the original structure minus the redundant reaction. So just have to copy the beam. So if we remove the redundant moment at A, so there will be no resisting moment there, so the beam will become a pin or a hinge. So it will become, from a prop cantilever, it will become a simple beam. Okay, so we'll just copy the load, the original load, so 160 kilonewtons, so 2.5 meters, 2.5 meters. So of course there will be still the reaction here, the reaction here. Horizontal reaction would be just 0 since we don't have any horizontal force. So by statics, so since the load is at the midspan, so this becomes 80 kilonewtons, and this is also 80 kilonewtons. Okay, so that would be the primary structure. Now what about our redundant structure? Okay, for our redundant structure, so we're just going to bring back the MA, the redundant. So that means, so we'll be having the same structure. So we have a simple beam with a length of 5 meters, and we'll be going to put it back, the MA. So there. Okay, so this is the primary structure and this is the redundant structure. Now, so due to this concentrated load, the beam or the elastic curve of the beam would be something like this. Okay, so if I draw a tangent line at A, the tangent line would be like this. So it will create a slope. Call it as theta at A due to the original load. So theta AO. Likewise, in the redundant structure, due to the moment at A applied, the beam will deflect or will have an elastic curve like this. And if I'll draw a tangent line at A, the tangent would be there, and I'll call this slope as theta at A due to the redundant MA. Okay, so but we don't know this MA, so we could relate this redundant structure to its similar structure. By this time, we will be imposing a unit moment. So 1 kilonewton meter. Okay, so for that 1 kilonewton meter, again, the beam will have an elastic curve like this one, drawing a tangent line there. So I will call this as slope, or slope at A due to that unit load at A also. Now, so I could relate these two. Okay, so by work method. So it could be 1 kilonewton meter times theta AA is equal to MA times the small FAA. Okay, so this is 1. Okay, now what would be the relationship between these slopes? The slope on the primary structure and the slope on the redundant structure. As we can see from the original beam, at point A, this is a fixed support. So we know that the slope there should be equal to 0, right? Okay, so therefore, so we have to write our compatibility equation or condition. So our compatibility condition should be the slope there, theta AO, when added with this slope, theta AA, should be equal to 0. Why 0? Because originally the point A is a fixed support and we know that the slope there is 0. Okay, now but what is theta AA? So this could be theta AO plus what is theta AA? Theta AA is there. So we have moment at A, FAA equal to 0. So from this equation, we could say that the moment of A is equal to the negative of theta AO divided by small FA. So this would be our compatibility condition or equation. So for us to be able to solve for the moment at A, we have to solve for these values. Now, so let's start with theta AO. So theta AO is here. So we solve theta AO. So as you can see, this beam is a determinate beam already. So how can we solve for the slope here? So we can use the methods that we have learned before. So we can use double integration method, area moment method, conjugate beam method, or even the virtual work method. So for now, I'm going to use the conjugate beam method. Okay, so for conjugate beam method, okay, so I'll be drawing the conjugate beam. So for this original beam, simple beam, the conjugate beam would be almost the same. So hinge roller supports. Then I'm going to draw the moment diagram by parts. Okay, so if I'll take this as my reference, this one, so what would be my moment diagram by parts? Due to the 80 kilonewton AY, so I will have a triangular moment diagram here. So 80 times 5 is 400. So that's over EI. And that would be away from the beam. So that would be an upward triangular load. And due to that 160, okay, so from here, 160 times 2.5 is actually 400 also. So I'll be having here 400 over EI, triangular load, which is directed downward or away from the conjugate beam. So for me to be able to solve for this slope, theta AO, that slope on the real beam corresponds to the shear. Diba? So shear at point A on the conjugate beam. And that is actually the slope AO on that real beam. Okay, so most likely the direction of this would be, since this is a bigger triangle compared to this one, so I think this would be downward. So you could just assume, if you don't know really the actual direction, and verify it later if it is correct or not. Likewise, since this is a roller, so there will be a reaction there, so let me assume it as downward also. But for this case, what I need is the shear at A prime. So how do I solve for this? So I'll take moment here. So say summation of moment at say C prime equal to 0. Let's say clockwise is positive, counterclockwise is negative. So what are the moments? So I'll have BA. So we have BA times 5, and that is counterclockwise, so negative. Okay. Then the triangular load sa taas, that would be clockwise, so plus. 1/2 the area of the triangle, 1/2 the base is 5 and the height is 400 over EI, and the moment arm from this point is 1/3 of 5. How about the triangle below here? So the rotation would be counterclockwise, so minus triangle 1/2, the base here is 2.5 and the height is 400 over EI, then the centroid distance from here is 1/3 of 2.5. Okay, so everything should be equal to 0. So from this equation, we're going to solve for the VA prime, and that will correspond to the theta AO. Okay, so calculating for that, so we'll have 1/2 times 5 times 400 times 5 over 3. Okay, then minus 1/2 2.5 times 400 times 2.5 over 3, then you transfer it, again, so we have 0.5 times 5 times 400 times 5 over 3 minus 1/2 times 2.5 times 400 times 2.5 over 3. Then we transfer it to the other side, divide by 5. So we got 250 over EI. Okay. So positive 250 over EI, that means that the direction here of VA is downward. So if we consider it in this sign convention, VA is downward. So VA is downward. This is the direction of the shear. And as you can see, the true sign of shear is counterclockwise. So therefore, I could say that VA is theta AO is equal to counterclockwise. So that means negative 250 over EI. So negative shear. Okay. Now what about for FAAA? Okay. So from here, so how do I solve for FAA? So again, using conjugate beam also. So our redundant structure is here. So the real beam is this one, so with 1 kilonewton unit load. Okay, so due to that 1 kilonewton unit load, so there will be a reaction here. So by statics, so say this is 5 meters. So if I take moment at A, this would be 1 kilonewton. This would be, how much would be this, so that it would be compensating the moment here. So it would be 1/5, because 1/5 times 5 is actually equal to 1, which is equal to the moment there. So by summation of forces vertical, if this is downward 1/5, this would be upward na 1/5. Okay, now that's the original beam. So what would be the conjugate beam? So hinge roller, so for the conjugate beam it would be the same. Then for this case, I'll draw the moment diagram by parts. So if I'll take reference here, so what will I get is the 1/5 times 5. So we have a triangular moment diagram there, so that would be 1 over EI. Then for that moment, taken reference here, it will produce a rectangular moment diagram, and that would be also 1 over EI. So the triangular load would be upward, that's away from the conjugate beam, while the uniform load rectangular would be downward, that's away from the conjugate beam. Okay, so I'm looking at this FAA. So this one FAA, and that FAA is actually the slope. The slope of the original beam corresponds to the shear. The shear here of the conjugate beam. Okay, now let me assume that the shear here is upward. Okay, so of course this also, there will be a shear also. Let me call it a shear at C prime. So but what I need is this one, because this will correspond to the slope, slope small f a A. Okay, now how do I solve this one? So if I take moment here, summation of moment at C prime equal to 0, take moment here. So what are my moments? So I'll have my VA. Okay, so VA prime times 5, the moment arm, that is clockwise, so positive. Okay, then the triangular load. About this point, the triangular load is clockwise also, plus 1/2, the base is 5, and the height is 1 over EI. And the moment arm of the triangular load from this point is 1/3 of 5. 1/3 of 5. Okay, now what about for the uniform load? It's downward. About this point, it's counterclockwise, so minus 1 over EI times 5 times the moment arm would be 2.5. Everything should be equal to 0. Okay, so solving for VA prime, so what would be the answer? It would be say 0.5 times 5 times 5 over 3. Okay, so that's for what? Then minus 5 times 2.5. Okay, then you transfer it to the right side, so that would be positive, then divided with 5, so I have 5/3 over EI. Okay, now what would be the true true sign of the shear at A? As you can see, this is positive. That means that my assumed direction upward is correct, upward. So this is on the left segment, upward. So the true direction of shear is clockwise. So this is VA prime, which is FAA, is positive 5/3 EI. Okay, so going back here using the compatibility equation, substituting values, so MA therefore is equal to the negative of theta AO over FAA. So that is negative of AO is negative of negative, so negative of negative 250 over EI divided by FAA is positive 5/3. Okay, so cancel lang yung EI, so that will become 250 divided by 5/3, so that would be 150. That would be kilonewton meter. So that would be the moment reaction at point A. Okay, so indeterminate structure, using method of consistent deformation, we were able to solve for the moment at A already. Okay, so moment at A. Now, I won't be discussing anymore how to solve for the remaining reactions, like the reaction at A vertical, the reaction at C vertical, because you can solve for these reactions by statics after knowing the moment at A. Okay, so let's say if you take moment at A, knowing MA, you could solve for CY. After knowing CY, you use summation of forces vertical, you could solve for AY. Okay, so that's it. I hope you learned something from this discussion. Okay, so good day.